Hi everyone and welcome to our Philly office. We have a very special NLP breakfast today, very hands-on oriented. And we are going to talk about how to build intuitions before we build model using, for example, vectorization and visualization. Who's best to discuss this subject is Emmanuel Amessen. Emmanuel has been working in multiple companies in the Bay Area. He led the AI program at Insight Data Science. Was it a program for PhD to start a career?
For PhDs and engineers, yeah, start a career in AI.
Okay, cool. And you directed more than 100 machine learning projects in this field. So thank you very much first to join us today. You took the train from San Francisco?
I did. Thanks for having me.
You're welcome. How was the commute?
It was good. It reminded me of my past days when I had to commute down for Insight. That was in Palo Alto.
Oh, okay. I thought it was in San Francisco.
We moved to San Francisco, yeah.
Oh, interesting. So before we jump into the subject, what drove you to write a book on this subject and come to explain it today?
Yeah. So when I was at Insight and when I worked as a data scientist and ML engineer in the industry, I feel like there was a lot of there were a lot of resources for people starting in the field to learn like basics of software engineering. There were lots of resources to learn sort of if you have a given data set, and you want to train a given model, a classifier, some regression, like how would you do that? There was a lot of progress with libraries like scikit-learn and TensorFlow being built to make that easier. But what happened when we had fellows that would join Insight and that would try to build applied products is that they would be able to do this. They'd be able to like say, well, if you give me a data set, and like you give me a model, and you kind of give me a metric that I should optimize for, I got you. But if they were given, we would partner with consulting companies that had like business problems. They're like, well, we're like a healthcare company, and we want to predict like readmissions in hospitals. Translating that product into like, the right ML approach, and then iterating on that ML approach, and like making a call about is that approach sufficient? Like, is it? How should we iterate on it if it's not sufficient was the very challenging part we found. And so most of our mentorship time was spent on that part. Like fellows were always good at training models and good at engineering around those models, but the discussions around debugging models, looking at your data, thinking about which model is the most appropriate, which approach is the most appropriate, were the ones that sort of took the most time, and I think were the most impactful for fellows joining the program. And so that's why I wanted to write a book that just more generally covered these topics for everyone that was interested.
Cool, thank you. You went with a couple of slides today.
I did. Do you want to dive in?
Yep, let's go.
Sure. This is I think a quote that illustrates this a little bit, which is, in theory, there's no difference between theory and practice, but in practice there is. What's funny about this quote is that it's by Benjamin Brewster. In theory, when you look it up, it's actually very disputed who said that. So even when it comes to quote, like you can't really trust theory all that much. But yeah, that's just sort of theme of why this is necessary. Is that in theory, it's very easy again to go from like business problem, model, get the right metric, ship it. In practice, as I'm sure all of you know, at Feedly, it rarely goes that way. There's many more steps. And so I just wanted to cover a couple of those steps.
Sounds good.
Let's just put these here, which is, this is sort of the two things that I talked about.
That's what you mentioned before.
Yeah. And so, there's both finding the right approach for a problem, which turns out to, I think, sort of change the story of whether you ship it in a week or in 2 years. One of the examples I give in the book is if you have like a search engine and you want to help people find things on a website, you can formulate your problem as like a language model where you try to guess like the next things that people will say when they type like, give me handbags or whatever. Or you can just build a classifier that will say like, oh, they're probably looking for like handbags versus shoes. And the second approach is like, it'll be done in 2 days. And the first approach, like, you'll be working on it for a few months. And so that's something that I cover in the book, but I think like we can leave it aside and maybe like, cover a few questions on there later. Debugging and iterating is the other part that I think is really interesting, which is how do you know what approach to choose? And then once you've chosen your approach, how do you know if it's good enough? And if it's not good enough, how do you know what's wrong with it? And sort of which steps to take next?
Absolutely. So that's also the kind of question we have in our interview, in our machine learning interview.
Awesome. Yeah. Then if you listen to this talk, then you'll just get a job at Feedly, right?
Yeah.
That's great. So here's a practical example that I've sketched out, and this I'll explain the slide briefly. I've just put it there for illustration. But a couple of years ago, I wrote a blog post that was talking about like classification for text. And the idea of the blog post was just to show sort of like a few methods of how you would do this in practice. And so, I started with something really simple, which is like you have, just like it's a binary classification problem for text, and you like use TF-IDF where you vectorize your text. You do like a logistic regression, which is like a relatively simple approach, and you get some number of accuracy. Let's assume, for the sake of discussion, that classes are balanced here, and then you can iterate. You can like go from TF-IDF to word to vec, like try a CNN. You can like try an RNN, et cetera, et cetera, et cetera. And so I showed these results, and people were excited about them. That was fine. And then somebody asked me later, like, okay, but if you were like, if this was actually your job, like if it wasn't just a blog post you were writing, what would you do, right? And what I would do is I would actually like spend, instead of spending a couple hours figuring out how TensorFlow does CNNs, I'd spend like a couple hours looking at the data. And so I did that. I put my money where my mouth is, and I just looked at the data for a while. And I spent, I timed myself. It was like 2 or 3 hours just looking at the data. And then doing that outperformed all the approaches. So that's the bottom arrow, which is I took the simplest model, like just logistic regression, but on a clean data set. And I gave it a model that was like just not only outperformed all of the, significantly outperformed all of the more complicated models you could have. So that's just like the motivation for why usually looking at your data is pretty valuable. I find that at most companies I've been at, a similar story tends to happen, especially because playing with fancy models is a very shiny project. So usually if you join a team and the team's been around for like a couple of years, there's been at least a few hackathons where they've tried like every single model you can think of their data. But it's not always the case that somebody's taken like a deep dive on each feature and tried to figure out like, why is this feature this? Is this like, should it be this? Is it wrong? If we fixed it, would our model improve? That sort of stuff. Yeah, so one way to think about this is if you're going to look at data, it's often, go label some data is often like I think a tip given to data scientists, but it's often given by people that have never labeled data. Labeling data sucks. It's really hard. And also there's not many processes to do so. Like many of the processes to efficiently label data are very well understood by companies that label data, like Crowdflower or Figure 8 or Scale. Like they know how to efficiently label thousands of examples, and they don't just like go down the line alphabetically, right? There's methods to do this a little bit more intelligently. So I think when you're cleaning a data set, when you're just like even inspecting a data set before you start working on it, there's value in using a little bit of sophistication. And so in the book, I go in depth into like multiple methods you could use to do this. But here I just wanted to point out one, which is most machine learning models that you can think of essentially act as vectorizers. Like what they really do that's really meaningful is they take, for NLP, they take text and they transform it at some point in a meaningful vector representation. Oftentimes many successive vector representations. And at the end, they like give you one vector, which is whatever the class you're predicting or an embedding or whatever you're trying to do, whether they're complicated or simple. And so that means that you can take any model, simple model, complicated model, and use it to just vectorize your data set. And why you would do that is because that makes your labeling effort infinitely easier. If you go from, I have 100,000 examples, or in this data set, it was 20,000, tweets, I think. And I don't really know what they talk about. I could do keyword searches to, I have this vector space and I can explore it. That starts to be much easier. And so to show you an example, this is just the simplest of vectorizations for this data set I was talking about. And what we're seeing here is word to vec applied, so pre-trained word to vec model applied to tweets. And so then we have
2 classes?
You have 2 classes. Mm-hmm. So basically the task itself, if you're curious, is you have tweets that use words like disaster, pandemonium. They use a common vocabulary, but some tweets are about actual disasters, like like an earthquake or something, and some tweets are about like Adam Sandler's latest movie. They're like not really relevant if you're 911 and you're trying to figure out what's going on. So the task is, can you separate tweets that are about actual bad things that emergency services should react to, or they're just using hyperbolic language. Anyhow, so here the vectorization I used was, you use word2vec and you average word vectors for a sentence, which gives you a vector for the sentence. This is like a very, very, very simple vectorization scheme and very far from the state of the art. But that's kind of the point here, is that you can use something relatively simple and then project it in 2 dimensions or in 3 dimensions using some approximation. So here I use UMAP, but you could use PCA, you could use TSNE. And what's important is like all of those methods that project like a 300-dimensional vector in 2 dimensions have many they break down the topology of the space in many ways. And so if you're gonna use that projection for a model, it's pretty risky because you might just be seeing effects of TSNE or effects of PCA, not actually what your vectors represent. But if you're just exploring data, the worst that can happen is you think there's a cluster over here, you look at it and you're like, oh no, actually these don't have anything in common. So it's fine to kind of use whatever at first. And then what's interesting is usually you'll see well-separated clusters. I picked this example in particular because I think that's one of the worst examples you can find, and it's still useful, which is in many cases you'll have very clear different blobs. Here in this one, you just have one big blob of questions or of tweets with both classes, but then you do have these outliers on the sides. And I haven't, because I want to keep the slides brief, I haven't gone deep into the examples here, but if you want, I can share the link with you of the other slide deck that has all of the individual examples of these, what do these tweets represent? But it turns out that if you look at them, almost all of those are either mislabeled or especially the ones where you see a blob that has 2 colors on the bottom right, which is both blue and orange. They're the same tweet. There's hundreds of examples of this tweet, and it has both labels. It has both labels, relevant and irrelevant. So you have a duplicated tweet that has 50 positive labels and 50 negative labels, which definitely isn't going to help any model that you train on this data set. So the main point here is you can quickly go through this vectorized data set, look at the outliers, and either correct them or use these clusters to inform sort of your modeling approach. So in the book, I use another example, and as you cluster things in this way, I use a Stack Exchange data set about writers. You find that all questions that are specifically about the English language tend to cluster together because they use the same vocabulary of or is this pronoun right, and that sort of stuff. And all these questions tend to have a relatively low answer rate. And so if you're trying to predict answers, it's a quick way to say oh, well, we should have a feature that detects whether this question is about language. Interesting. So that's it. That's the first. There's sort of 2 techniques that I want to cover. That's the first one, which is pretty simple, which is vectorize and explore your vectorized data.
So the 2 takeaways here are you could find mislabeled data very quickly, very easily.
Yep.
And you can start having some guess about the model strategy.
Yeah,
and what would make you decide of a particular strategy?
Yeah, so I think the first, before even sort of the model strategy, you can it's a modeling strategy, I guess, which is you can think of features. That's usually a very good method to think of just when you're thinking of generating features. A lot of these sort of clusters or clumps of data points, if you just visualize 20 of them, you'll see things similar to what I just mentioned. Oh, all of these questions are about language. All of these tweets, 12 exclamation points in them. Oh, all of these, they have certain commonalities, which can just lead you for your first model to just pick that feature and add it as a counter or as a Boolean and just add it to your model and see if it's. And so this is more of a feature generation stuff. You can also think of which models you use, because if you have sort of, if looking at these, you see that all of your relevant examples have long-term syntactic structure or sort of complex semantic meaning, then you might be inclined to use a more complicated model. But mostly I use this as a first feature generation step, and it works well for these kind of things. And you can do the same, by the way, for importantly for any data, right? So here, obviously this is an LP meetup, but vectorization works for images. You just vectorize the images in a common space using a pre-trained ImageNet model, and then you can see with fellows, oftentimes you'll see oh, here's a bunch of low contrast images. Here's a bunch of images that are super saturated, and like think of pre-processing methodologies to help with that.
Cool.
All right. Moving on, you can do the same thing, and this is, I'm cheating here because I'm really showing the same slide, but this is a method that I haven't seen or used much outside of Insight, but every time we use it in Insight, it worked really well. So let's say you've trained a model. So you went through your data set once, you built a few features, you're saying, okay, well, these features look reasonable, and I'm deciding to use a simple model to start, so I'll use like, sort of like naive Bayes on count vectors or something. And then your model reaches, I don't know, 80% accuracy. Like, what do you do next? Should you just like a lot of the default mode thinking, I think of a lot of people that follow maybe in my classes is like, well, you try a model with more capacity. It's like, okay, well, you try a model with more capacity. At some point, like, you're going to run out of capacity, right? You try GPT-2, and then like,
and you just look at the score.
Yeah, right. The score tells you something, especially if the score is a good score to look at. That's a whole entire problem. If the score aligns with your business goal, then it's good. It tells you whether you're good enough or not, to a certain extent. But the question of what to do next, I think, is still a salient one. It's still one that's relatively less explored in papers and in research. And so I found that using the same method, and by the way, this is something I stole from Robert Monroe, who was briefly a technical leader at Crowdflower, where they would do this to do active learning and train models better, is you take your first model and you run it over your whole data set, or if you want, you can still split train test. You can run it over train, for example, and you color each point by whether your model got it right or wrong. And so a lot of times, and again, I like this example because this is like one of the worst ones, you'll see like different clusters, but even if you don't, you'll be able to explore areas. Like here in this chart, you can probably see areas that have both orange and blue, and you're like, okay, well, why do these questions that are like super similar, vectorize in the same way? Somehow my model gets one right and one wrong. Like either they have, again, either there's another labeling error, which looking at this, you can find many more, or just, when I say labeling error, it doesn't just mean like there's a labeler that made a mistake. I'd say like your data is corrupted in a way, right? Like even if you have an automated way to like generate your data, like something happened, like the way you reconcile the data was wrong. Or yeah, you'll find meaningful things that your model isn't picking up on once more, right? And so again, you just vectorize it and sort of like go through the vectorized representation. Once the best way is like to go sort of like cluster by cluster and then just like plot 10 examples. And you'll almost always find sort of like, oh, okay, so for these examples, like very clearly, my model is overfit on a certain feature. That's like, I think the most common thing that comes from this analysis is you'll say like, okay, well, here, all of these questions share this in common. They're all like, an example from the book is like a very simple one. They're all over 500 characters. And my model's just decided that like all of those are positive examples, no matter what, right? That's very clearly not true since it got half of them wrong. So we should like have additional features that should like help disambiguate those questions. Like, okay, like out of those long questions, maybe the existing features are all biased. So can we make new features that like capture the differences between long questions better? And that's just a high level approach. But I found that to be extremely useful. And in terms of iterating, every time you have a model and you decide on your next model, just like doing a deep dive on errors is a good idea. So this is one way to do a deep dive on errors. There's again like many others I cover in the book, and there's like sort of the usual like calibration curves, confusion matrices, and like looking at most confident, least confident examples. But yeah, I think in general, these are sort of the useful tools that we've seen a lot of data scientists not have when they come into the field.
Yes, sounds good. So it's pretty similar to the approach you described before, but this grasp different patterns.
Yeah, and so a lot of this is used in practice again by like data labeling companies, which seems to use like a completely different set of tools from what other ML companies use, but like a very, I think, valuable and interesting one. But one way you can use this is if you have to label 100,000 examples, you train your model, you label 1,000, you train a model, and then you run your model on the like 99,000 you didn't label, you cluster that, and you label the clusters that it gets the most wrong in a proportion, right? So that's like a very quick way to label a lot of data that basically uses this approach.
I have a question. Do you really use the visualization in practice, or do you, because for example here, where would you look at this image to say, because it looks like just a big blob, but I mean, I understand that like in your console, you might like display the biggest clusters and look at each of the examples individually and say, okay, this is very heterogeneous.
Yep.
So I'm going to look at it. But from the visual perspective, do you have sometimes cases where it's more
more separated?
Yeah, perceptive.
Yeah. That's a super good question. So a couple of things there. One, as I mentioned, like I like this example because it's one of the worst in terms of like, usually you'll see many more clusters. And what's interesting is if really you're not able to separate it visually, like here, like it's pretty hard, using a more elaborate vectorization method usually will work because it incorporates outside context. So usually if like this is really too blobby, I'll be like, okay, well, let's actually use like maybe like some pre-trained model. Right? Okay. But to your point, a lot of the blobbiness can also be due to the dimensionality reduction that you use, right? Like these are 300 dimensional vectors, like they look like a 2D blob, but it doesn't mean that there's not meaningful ways to separate them in 300 dimensions. And so what can be useful is running clustering on the full vectors and then coloring this plot by the clusters. So that makes sense. Then like you might have this blob, but then like there's a very clear cluster that's like at the bottom. And again, the point here is to guide your exploration, right? So once you have clusters, it's just like, the way to look at it is like zoom into those clusters and look at these examples. That might say, there's not many tools to do that, unfortunately, right? There's like TensorFlow lets you train anything you want, but if you want to look at a cluster of data like that, you got to build your whole custom thing. I have a notebook that's linked in the book that uses like bokeh to do this very easily, where like plot your data and then like plot these colors and then just like let you zoom in, and when you hover over examples, it'll show you like what they actually say. Unfortunately, I found that like building custom stuff like that is necessary for those sort of things. But yes, so coloring them with using a clustering algorithm that works in 300 dimension helps with separating the blobbiness. And for those examples, for this one in particular, one thing that works really well is to look at like those, you see those small like outlier-ish like clusters on the side. If you look at those, especially the ones that are like two different colors, when I looked like a dozen of them, and it was almost always, either the model making an obvious error that I couldn't correct, or like a labeling snafu. Cool. That's most of it.
Thank you very much.
Thank you.
By the way, we pre-ordered the book. When will we receive it?
Oh man, good question. It went to the printers on Friday, and so I am told that printing a book takes 3 weeks.
Okay.
I have no idea what's involved with that, but it takes 3 weeks, and so it'll start shipping in 3 weeks. If you want it on Kindle, it's available now.
Okay.
Cool. Looking, I think, you gave us a little bit of a glimpse of, what your book was about, and this was really, really interesting. Got me excited about what the rest of the book. But what's the elevator pitch for the book, or can you give us a little bit more of the table of content or what people can expect from the book?
Yeah, can I sell my book? Yeah. Okay, so the pitch is, again, what I said is at the top, which is, other than just training an ML model, or like doing engineering, like this is about how you go from an idea that either like your PM hands to you or that you have for a side project to like a deployed model. And it almost purposefully just ignores like a lot of the like CLF.fit. It's like, that's fine. You have docs. And so the 4 big parts are various ways to go from like, here I have this goal to like different machine learning approaches, and like how you would compare both in terms of like what model should I use, what data set should I use, and which ones may be hard or easy. That's the first part. The second part is sort of like diving deeper into data and how you explore it to generate your first hypothesis of how you'll work once you have a data set. The third part is all about debugging. It's like, what do you do once you have a model and like, you want to find the next model? So like some of the things we covered here and many other aspects, but also what do you do if your model doesn't work? I think especially as you go for like more complicated pipelines, everybody's just had this result of like, these predictions seem random. Like I have no idea what's going on. It's like tools to debug that efficiently. And finally, the fourth part is about like deployment and just different like both deployment methods and sort of like things that I find that people don't necessarily know when they're starting off in the field that you probably do it at Feely, for example, which is like, okay, well, how would you go about caching results for like machine learning? When is caching meaningful? Like when do you have to be careful about caching? And sort of like just general concerns, and a few like examples and stories about what can go wrong when you deploy models. You might have horror stories here, like you tell them the corridors of the office, I don't know, but there's always like horror stories of, we shipped this model and everything looked good, but somehow like all the metrics just went down. So how do you try to catch that early? So that's the pitch for the whole book. It's teaching you each of these aspects, which I find that when I interview people or when you look at people that contribute the most to the team, it's often on these topics. And it trusts that like the people that read this book, if they're curious about like how to use TensorFlow, they can Google like the TensorFlow tutorials. It's written to be accessible for anyone. So there's code snippets, and in fact, like you build a whole application throughout the entire book, and the application is like on GitHub, you can use it, it's there. But if like you're not comfortable with code, you can just skip the code snippets and you'll be fine for most of it. So the goal is for also like PMs that are interested in AI to be able to benefit from it.
That's very cool.
Thank you very much again, Emmanuel. And round of applause.